We have with us right now, is he around, Nick, I hope? He's going to discuss water mist as a safe, effective, environmentally friendly, cost-effective solution. I'd like you please to welcome Mr. Nick Link, CEO at FireBug Group. Nick is originally from South Africa. He's been based in the UK for 13 years, where he's been involved in patenting of various misting technologies, including low, medium, and twin fluid supersonic designs. He was involved in developing a misting decontamination compatibility for M15 and has been extensive experience across Africa, Europe, Asia, and the Middle East. Ladies and gentlemen, let's welcome Mr. Nick Link.
Thank you very much. Major General, professional colleagues and guests, thank you very much for the invite today. I'd like to start by really just giving a short summary of what I'm going to cover, because it's something that is not a common topic around the world. People think that mist, water mist in itself, is just a fine water droplet. So I'm going to get into a little bit more of the science behind it, how it physically works, how it actually extinguishes, and the different types of mist. Because believe it or not, they are different. This was the last person that didn't pay attention during one of my presentations. So let's listen. I'm just joking. This is some testing that was done for the motorsport industry. That is a supersonic nozzle producing droplet size of around about 25 microns at 4 bar pressure. Please turn the sound off. So the droplet size is 25 microns, okay? And it's producing it using supersonic technology, which I'll explain in more detail later. But the critical thing to notice, it was 4 bars of pressure. So very safe for the person, the operator, etc. Right, so let me cover some of the mist basics. First of all, mist dates back to the 1950s. But what really held water mist back was in the 1960s, Halon was developed, which of course was an elite firefighting solution, and nobody needed to look any further. The second thing that held water mist back as a technology was the sprinkler industry and chemical manufacturers. Now, I don't mean that in a negative way. Sprinklers are life-saving devices, as Peter was talking about this morning, as Steve McGurk was talking about this morning, as Engineer Katiba said this afternoon. Sprinklers have their place in the market. But when we have such a huge industry that is relying on producing foams or gases or sprinkler heads, to move to a technology which reduces that demand, of course it's going to be stifled. Now, because of the environmental times that we are facing at the moment, every country around the world, now I'm dealing in more than 50 countries, so I have a pretty good understanding of the different expectations. The common topics are environmental aspect, reducing of water, reducing of manpower, better and safer firefighting, and of course trying to do this within a tighter budget. So of course, what topic comes back is using water. So now all the manufacturers around the world and all the fire services, civil defense, military, everybody is now talking about water mist, as you've already heard a few times today from Steve McGurk talking about his compartment fires. So back to the basics. There's really 3 critical elements that we need to look at with water mist. One is the droplet size. That's measured in microns. The second critical thing is the pressure. So there's 3 pressures, 3 types of way we can produce. One is high pressure, which is above 60 bars. This is the most common. It's the easiest to produce. The second is medium pressure, which is between 12 to 59 bars, and then below 12 bars. Now, why that's important? Because the first important aspect is the micron size. And if you're not able to have the right technology, the pressure affects the droplet size. The third element, which is probably the most important, is what we call kinetic energy. So those of you engineers in the room, you'll understand this term. So I'm going to cover kinetic energy in more detail. So in order to have a super mist, which is able to cover all the classes of fire, A, B, C, D, E, F, we need to have the correct droplet size and the correct amount of kinetic energy. So the small droplets are absorbing the heat because of the surface area, which I will discuss. But if you have small droplets are very difficult to have any energy. So in other words, the small droplets are just floating in the air. So of course, when we have a large fire, the heat radiant barrier, which is coming off that fire, the mist is unable to reach the fire. So within a few meters from the fire, it's converting to steam. It's not actually penetrating the fire. And if we go with larger droplets were much easier to create the kinetic energy. But if we have larger droplets, they are too heavy, they are falling to the surface, and they are wetting the surface, which means they are fighting the fire in the classic way, just like any normal water spray system, which is inefficient. So just by this image, you can see the smaller droplets are beginning to float, and the larger droplets are sinking. So the further from the nozzle, you've only got bigger droplets because they're the only ones that have got the energy to reach that distance. And even further beyond that, you've only got small ones which have no energy and are just burning off. So this is where mist gets its gray area. NFPA, according to 750, define water mist as anything from 0.1 micron, which is steam from your kettle, to 1,000 micron, which is your shower at home, a typical sprinkler type system. So according to NFPA, that entire range is water mist. So anyone who's making a droplet size within that category can mark it as a water mist. But you can imagine, being experts, the firefighting performance from 0.1 micron up to 1,000 micron, the firefighting performance is completely different. 0.1 micron is absolutely useless for fire. 1,000 micron, you're not going to extinguish a B-class fire, an oil fire. You're not going to put it on an electrical fire. You're very much defined by that droplet size. Right, why is the droplet size so important? Here's the science behind it. If you could imagine 1 liter of water as a droplet, it would be roughly this size. Okay? So that's 1 liter of water as a single droplet. That gives you a surface area of 0.05 square meters. Now, surface area is solely responsible for the exchange of heat. So it's the surface area that's responsible for the absorption. So if we took this 1 liter of water, it's a droplet this size, and we break that into 25 micron mist, as you saw in the first video. So imagine smashing this droplet into 25 microns. You get 122 billion droplets. Okay? So looking on this side, you can see that gives you a surface area of 240 square meters from 1 liter of water. So for anyone who's got any engineering ability, you will understand that the surface area of 0.5 versus 240, the 240 is superb for extracting heat from the fire. 0.5 is not very efficient. So if we look at our traditional firefighting techniques, or our traditional firefighting equipment, such as the guns on your fire trucks, sprinkler systems, etc., most of them are relying on the 0.05 square meters, which means you need a lot of water to extinguish. So how does mist actually extinguish the fire? It extinguishes in a very different way to any other agent. So the way it extinguishes if you look on the left-hand side of this image, it pulls the fire triangle apart. So if you look at a conventional system, a foam, a CO2, a powder, a water, a CO2 is knocking one side of the triangle. And the cooling to remove the heat is a secondary action. If you're using foam or powder, always you're affecting one side. And then as a secondary action, you have, and usually it's a chemical such as powder, where the powder is burning and converting to nitrogen or carbon dioxide. Where mist is completely disassembling it. So how does that happen? This is what actually happens. You have a lot of very small droplets, right, with a lot of density. They enter the flame. This is the important part to pay attention to. They don't wet the surface. They're coming into the flame, and on entering the flame, you can see on this image, they are converting to steam, and they are evaporating, which is rising. So it's not leaving water on the surface of the fire. It enters the flame, converts to steam, and rises. When it converts to steam, steam is an expansion of the water by about 1 to 1,620. So if you're putting 1 liter of water mist into this fire, you're multiplying it by 1,620 times when it converts to steam. So what actually happened? The droplets went into the flame. During the conversion to steam, they extracted the heat, the energy from the fire. Once they converted to steam, this steam has multiplied in size and is an inert vapor. So it's removed the oxygen from the fire. And because of that cooling effect, it stopped the layer of free radicals. So that gas layer is prevented. Because we've cooled the fire to such a level, it's not reproducing more gas. So in other words, it's affecting all three sides of the triangle. Let's see. So just some interesting statistics. 335 kilojoules of energy is used to heat 1 liter of water from 20 degrees to 100 degrees. But this is now where the mist comes into in a fire situation. 2,257 kilojoules of energy is used to convert that 1 liter into steam. So the absorption of heat is incredible. 50 micron mist has the cooling effect of 7 kilograms of ice. Right, so very quickly, what actually happens in a fire situation? The fuel is heated, becomes hot, and begins to decompose. When it's decomposing, it's creating a layer of gas, which is known as free radicals. This layer of gas has a lower ignition temperature than the fuel itself. So this gas is what's actually burning. Okay? So when we are coming with the mist extinguishing, what we are actually extinguishing is this burning gas. We're not depending on wetting the surface. Right, so this is some cooling. Actually, this was done as part of some of the testing with Steve McGurk that you spoke to this morning. Can you play the video? Alina, can you play the video, please? So this was a compartment fire. In around about 40 seconds, so the fire was heated. I think it reached 582 degrees C. We drilled a hole in the door, and we introduced a water mist droplet of around about 55 microns. The system is now activated. Look at the cooling effect. So within around about 45 seconds, it goes from 582 to 182. 45 seconds and less than 20 liters of water. That's the critical part for the civil defense fire and rescue market. So within 45 seconds, you're in a much safer position to send your firefighters into a building. Now, this is a very spoken topic around the world with all the fire and rescue. Every civil defense I've been to, its hot topic is to be able to fight the fire from outside of the building. As you've heard, I think Peter was mentioning it this morning, Steve McGurk was mentioning it this morning. Right, so moving on quite quickly, this was some more testing on cooling. So this was a plastic fire, mixed plastics, floor tiles, vinyls, rubber. And you can see the fire reached, on average, around 500 to 600 degrees C. Once the mist system was activated, within 30 seconds, it's reached 50 degrees C. 30 seconds. So this is the oxygen content inside the flame. Right? So probes were measured inside the flame. So you can see the oxygen level is sitting around 21%. On activation of the system, it's reaching down to just below 17%. Now this is just inside the flame, not the whole room. So how is mist formed? Basically, there's under the three pressures. If we look at high pressure, the most common one is swirl chambers. So you've got a nozzle which has very small orifices, very small holes, and inside you have different swirl chambers which basically accelerate the water through this small hole. And it is simply working on something like your car washer. It's blowing the water through these small holes at high speed. There's some pros to that, there's some cons to that, advantages and disadvantages. Medium pressure is usually working on the same technology or colliding streams. So this is a nozzle which has colliding streams. I don't know how clear it is at the back, but you can see you've got a hole on the inside and a hole on the outside. And the streams of water are colliding at each other, and that is creating a mist. And then there's another technology under medium pressure, which is being used in the market now, which is effectively mixing the nitrogen inside a cylinder and the water inside the cylinder and transporting bubbles all the way to the nozzle, which we call a rotor system. The third type of technology is called, it's low pressure, but it's usually done under twin fluid. I've never come across anybody yet who's able to do low pressure with single fluid. So what does twin fluid means? It means you have one stream of air or nitrogen and one stream of water, and they are colliding. Is one way. So this can go down to 4 bars of pressure, and you can get a reasonable size mist, anything from 50, 100 microns. But the most high-tech of all the mists is ultrasonic. So the way that works is it's introducing 2 layers of air inside the nozzle, and they are accelerated to a high ultrasonic speed, and the noise of that air traveling inside the nozzle is causing a vibration, and then the water is injected through the middle. And of course the water cannot travel through that noise barrier without breaking into small droplets. It's a lot more precision engineering, it's a lot more high tech. This is the type of nozzle, ultrasonic nozzle is what is used by most of the manufacturers around the world in data centers, IT suites, chemical laboratories, places where you need a very, very fine droplet. Supersonic nozzles can reach anything from 5 microns upwards. 5 microns is useless for fire, but it is used in dust and decontamination. So this is what happens with a poor quality mist. So this is around about 60 microns, so the droplet size is absolutely perfect. But the pressure is too high and the kinetic energy is too high. This was an Asian company which asked me to come and have a look at some of the technology they had. And you can see, it's absolutely useless. If that was on any fire trucks, we would be in trouble. Why is it not working? It's a 50 micron droplet. What's the problem? I'll tell you the problem. The energy is too high. It's penetrating through the flame and touching the surface. When it's touching the surface, the droplets are too small to create a wetting effect. Mist does not fight the fire by wetting. It fights the fire in the other tech ways I explained to you. So relying on wetting the surface, you need a lot of water. So as soon as you have too much energy, you're wetting the surface and mist becomes ineffective. Okay, so I'll now show you almost identical fire with the right droplet size identical, but the right kinetic energy. Play the video, please. This was extinguished with around about 2 liters of water. So you can see it converting to steam. There's almost no water on the floor. Do you see the totally different effect, but the same size droplets? I'll move on because we're under pressure with time. So some of the applications can range from mobile to fixed installation, but what are the advantages? Lower water consumption, a much smaller footprint. Because you need less water, you can have smaller vehicles. If it's in a fixed installation, you can have smaller tanks. Less mess. So you don't have the risk of fire water, which you have to clean up after the fire. You don't have the flooding risk where you're having water going into basements or cable tunnels. The bigger coverage area. So a mist nozzle versus sprinkler head. The mist nozzle is significantly bigger coverage, so you need less nozzles. It's safe on electrics. So I get some strange looks around the room. You can see the testing done on the left-hand side. This is basically done with an electrical plate. This is done by various different laboratories around the world. And the mist is sprayed at the electrical plate, and the conductivity is measured. Now, I've come across nozzles in the market which are rated up to 540 kV. Some of the smaller nozzles are from 35 kV. For example, IBM are protecting some of their data suites and some of their IT server rooms with water mist. So if it's good enough for IBM, it gives you an idea. No thermal shock. So if you are spraying the mist onto a hot boiler, a hot turbine, a hot engine, you have a different effect that you would, if with water or with CO2, you have this thermo shock where you're going to crack the heads or cause warping of the engine. You don't get that with water mist. It's safer for the user because mist is creating a radiant barrier. If you saw the video, you were able to see how close the firefighter can reach, because the heat is unable to come through the mist to the firefighter. It's much simpler for training of staff, especially for civil defense from a fire pump, a fire truck. You don't have to worry about different pulsing techniques. Compared to a gas system, you don't have to worry about the volumetric calculations. So if you're doing FM200 or any different gas systems, and sorry, I'm not running down FM200, please take that off the record. If you do the calculations based on the percentage and the contents of the room change, because they put some more equipment, the displacement of the room changes. And it should change the design of the system. You don't have that effect with mist. And with open spaces, such as cable tunnels, normal tunnels, open conveyors, this type of situation where a normal gas or a normal system might have difficulty. Right, so what are some of the systems? So usually, majority of the systems, the fixed installations, can be integrated with any mechanical detection. Usually they can be integrated with pneumatic detection, electrical detection, any early warning system. Basically, they will work in the same way that you currently have any other system. There's 3 types of operation. One will be a cylinder-driven. So you've got a nitrogen vessel driving the water, or you've got a pumped system. The tank can obviously be standalone, or you've got a stored pressure where the mist is inside a cylinder. So this is an example from a German company. Comparing, this would be the sprinkler installation. I don't know how clear it is, but this I think is 21 cubic meters of space required for the tank. The exact same mist installation would require 12.5. So of course the space saving and especially collateral damage afterwards. So some rapid response solutions. You can see in the top left-hand corner, this has actually been in development with Steve McGurk, who was talking this morning. This little fire vehicle that they've developed is a 4x4. It's using some misting technology and some conventional firefighting technology. They have a backpack fitted in one of the lockers, which they use for all their first response fires, tires, rubbish bins, etc. Please play the video. So this very quickly is a small rubbish fire. It was extinguished with around about 300 milliliters of water. You can see because the steam is working. So I'll move on because time is really short. Please play the video. So this is tires. You'll be familiar with how difficult tires are to extinguish. This was around about 6 tires, dosed with diesel and petrol, pre-burnt for about 7 minutes. It was extinguished with 1.9 liters of water. 1.9 liters. I'm sure with most of your technologies that you're probably using at the moment, that would be 300 to 500 liters as a minimum. Right, some of the larger firefighting vehicles which are being tested around the world at the moment. We've come across them in Taiwan, we've come across them in Japan. Full fire trucks using misting technology. And if you look on this images on there, this is the much discussed Cobra system, which you can see by the image is allowing the firefighter to extinguish without going into the room, basically making a hole, injecting mist into the room. So a portable mist extinguisher. This particular model is EN certified. It's the only extinguisher using water that is able and certified to extinguish Class A, B, C, D, E, and F. Not all classes of D, please note that, so metal fires, not all classes. But the one which is a very hot topic in Europe and the Nordic countries at the moment is lithium fires. Because we're moving to hybrid cars, hybrid buses, and they all have lithium batteries. Mist is exceptionally efficient at extinguishing lithium batteries. Water mist kitchen systems. There's a few of them on the market. So this is extinguishing fat fires, oil fires, with just water. No additives. So the cleanup time is much quicker. This is a conveyor fryer. This is actually in Dubai. The peanuts are dropped in one side. It goes through a hot oil conveyor belt. On this one you can see nozzles are fitted here, and the detection is all the way along. Just water mist, nothing else, no additives. Some industrial applications. On the right you can see a transformer that's on a mine in South Africa. On the left-hand side you've got a conveyor. Wind turbines. So in the UK, they're using water mist in all the prisons now. They removed conventional hose reels. There is no normal water hose reels in any prisons in the UK. They only use water mist now. Oopsie. The one on the right-hand side is a standalone mist unit, which some of the fire and rescue services in the UK are using for places where there's old people that are living that are unable to leave the bedroom. So it detects from the normal screw and smoke detector. Right here we have a tunnel situations. IT data centers. Certification, I'll just go back one step. I just need a few seconds on that. There's a wide range of certifications available for water mist. VDS, UL, FM, they all range depending whether you're competing on a sprinkler type installation or whether it's industrial. Dust suppression. Water mist is used for dust suppression. Normal extraction systems can be said that you are moving the explosion risk from one area to another, where water mist, you're actually suppressing it. Just some examples of dust suppression in grain silos, biomass. And that's it. Thank you very much for your time. I hope you've learned a little bit about water mist, that they're not all the same. I'm available for questions afterwards, and we see where we go. Thank you.
Thank you.